of the 4MD task group. So I hope that's clear. It should be quite a high-level introduction, just going through the principles themselves. So what are the FAIR principles? So they were introduced in 2016 to help all stakeholders in science overcome obstacles to data discovery and reuse. I think if we all work in the metrology field and we all work in adjacent fields to metrology, we know that there are a lot of siloed data processes. People are processing data and have their own data models and their own setups for how they structure, name, access data. And if you've ever tried to look at anybody else's project that you're not involved in and that person's not there, it sometimes can be a bit of a labyrinth trying to understand what to access where, what is the context to this particular experiment, what's the context to this data, some of that additional information, that metadata that would make that information rich and you able to understand it is missing, and you would need to actually speak to the person themselves to understand that. If they can remember it, you may be looking at experiments from quite a long time ago. So the FAIR principles try and foster that awareness that these digital objects deserve more care and attention than we're generally given. The overall goal is that data should be easier to discover, understand, and reuse. An important point is that it's both for people and machines who will be accessing this data, because these principles will allow automated data discovery as well. It's not just about human beings being able to understand it, it's about machines being able to have all of the information necessary to them. I think this is an important point, this next one. They are principles, they're not exhaustive standards or laws. Sometimes I'm slightly uncomfortable with compliance as a term for the FAIR principles. Yeah, there's a lot of nuance into how you should enact some of these ideas, and I see them as aspirational principles. And I think in general, it's a way to get everybody involved in data management, have everybody speaking the same language, which really is a key element to interoperability. So what does FAIR mean? Data should be findable. So machines and humans should be able to discover that data using identifiers, metadata. Data should be accessible. Retrieval must be possible through clear and open protocols, even if access is restricted. Data should be interoperable. It should use standard formats, controlled vocabularies, and shared semantics, so that different people can access and understand what's going on. And data should be reusable. So data sets should have that context, some uncertainty information, the licenses that were used, everything that's necessary that someone who's unfamiliar with the actual experiment or the process of generating that data, everything that's necessary for them to reuse and reinterpret that data. A key point I wanted to make here is that FAIR data is not open data. The goal is not that, despite one of the principles being accessibility, the goal is not that everyone can access all data at all times. The data should be as open as possible and as closed as necessary. There are many reasons why data should not be released freely. It can be ethical, legal, or commercial reasons. It's more about how open should we be able to make this, and if people need to see the data, what is the best way of allowing them to do that? And I think that's quite an important point, is that it's not about just giving all of your data to the internet in a nice way. It's about structured data management. And yes, why should we care as metrologists? I think that example I gave in the beginning of everybody working in, everybody will have experiences of people working in siloed data processes. Metrology is undergoing a period of digitalization with the likes of digital calibration certificates. You'll hear something later on about the digital representation of the SI. These tools work if we are able to have the data infrastructure that facilitates the sort of transparency and traceability that we associate with metrology, that rigorous documentation that we associate metrological processes. We know that there's a large amount of data being generated from instruments, and The only way that data doesn't become completely redundant is if we have some structured management to that. And I'm certainly seeing industry and funders expecting alignment to these FAIR principles, and we are certainly seeing some internal and external pushes for alignment to the FAIR principles. And I think for the hot topics that are emerging in digitalisation at the moment, automation, digital twins, obviously cross-lab comparisons, and the emergence of AI processes, FAIR adoption of the FAIR principles will aid all of these elements and make the process smoother. So I'm now going to go through the principles themselves. I hope it's not too dry as I describe this, but I think it's important to go through in a bit of detail what the principles are themselves. So these are the principles in detail. So one, metadata assigned a globally unique and persistent identifier. Generally, when we produce research outputs, we will attach digital object identifiers, or DOIs, to those to identify them in a globally unique and persistent way. So that's an example of something that would satisfy F1. F2, data describe rich metadata. So that data documentation or metadata is data about data. So how do we describe the data? Which study materials are we using? What process at each stage of the data lifecycle are we looking at? The planning, the preparation, just all of the data that helps you to understand what that data actually means. And then going on to F3, the metadata clearly and explicitly includes the identifier of the data it describes. So I've described DOIs as something quite common to research data that we produce. So that unique identifiers, that can be included in the accompanying metadata that describes where the data actually is. So for example, a DOI points to a landing page, it describes the published item, any restrictions on data access if applicable. So it's a nice example of something quite fair that we all sort of use. And metadata are registered and indexed in a searchable resource. So generally these resources tend to be online, publicly accessible repositories or archives that allow individuals to create metadata records. So again, DOI is a perfect example of this. Sorry, I'm getting a little bit of background noise, so if people could put their microphones on silent, please. So if we're to look at this in metrology, I think that calibration data sets, digital calibration certificates, are a fantastic example of this, using persistent identifiers for calibration data sets. If we want to provide rich metadata describing instrument conditions and traceability chains, create searchable catalogues of data sets without exposing the sensitive content, and just trying to ensure that the metadata we're using in this metrological data chain supports that automated discovery and assessment. And you will hear some more about that as the webinar goes on. I'll perhaps go through this in slightly less detail because I've looked at my time so far. So for accessibility, this is all about how do we access the data in the most open and free manner. So one of the ways we do that is have metadata retrievable by their identifier using a sort of standard protocol. So referring to the sort of technical and organizational mechanisms used by organizations to create and offer unique persistent identifiers for outputs. Ideally, that protocol that you're using to access the metadata, if possible, is open, free, and universally implementable. So it's not subject to any sort of technical, organizational, or financial barriers that would prohibit somebody from accessing that data. The protocol should allow for authentication and the authorization procedure where necessary. As I've described, we are not trying to make all data accessible to everybody at all times. There should be appropriate access controls that facilitates the correct people being able to access the data, but it should be in place so that if that person is there, they are able to access the data itself. And A2, which I always finds quite an interesting one, is so it's metadata is accessible even when the data or it's no longer available. There are many reasons by which we would destroy data. Yeah, could be ethical, legal, commercial, but that metadata that allows you to understand what was generated when allows you a richer picture of what's going on and allows people to understand that process. So I think there are many ways we can aid accessibility in metrology. As I wrote this, I realised a lot of what's written here can be generally applied to data processes as well. But providing stable access protocols such as HTTPS download, APIs, repository systems for accessing data, describing those access conditions clearly, because that's not always clear, and normally you have to speak to IT and people like this to understand your access procedures, but understanding the licensing and authentication of your data. If your data is stored securely, then ensuring that it still remains accessible via these metadata that I've described, and enabling machine readable access to support automated workflows, so allowing that data to still be interrogable. So we've all probably experienced times where data is stored on somebody's personal hard drive, and if they're not in the office, you cannot access that. So having data stored somewhere that can be accessed is vital. And now I think probably the most difficult of the FAIR principles to implement is interoperability. So how can different systems or different people understand the data and access it? And so I1 here describes using for our metadata, using a formal, accessible, shared, and broadly applicable language for knowledge representation. I think the SI, the digital framework, will probably touch on this point. A lot of people are developing ontologies and taxonomies that help describe data in a way that can be interoperable with other processes. Having metadata use vocabularies that follow the FAIR principles. So people should aim to apply community accepted, approved, and controlled vocabularies that are implementable without any major technical barriers and adhere to all of the principles that we've described so far. And I3, and I think this is quite important for not having siloed data, is that metadata include references to other metadata. So having, if to continue that example of DOI for your research output, it may be that you have a network of linked outputs using unique identifiers like DOIs, ORCID, that allow people to sort of understand how this data connects to other metadata and allows them a richer picture of the overall system itself. So if we're to look at this for measurement data, some of our goals should be to adopt shared file formats and data structures across laboratories, using SI units consistently throughout data sets and metadata. So obviously there's been a lot of work in developing the digital representation of the SI units. Like to align data with digital calibration certificate standards and metrology ontologies, and sort of high-level ontologies and how they blend into those. And yeah, to try and support automated integration into quality management and process control systems. And the final principle is to be reusable. So I think this builds on a lot of what's been discussed so far. We want metadata to be richly described with a plurality of accurate and relevant attributes. Metadata should be released with a clear and accessible usage license. So that instructs other potential users of your research output on how they may have been used and how they may use it themselves. Metadata are associated with detailed provenance. So that refers to the sort of history of the research output and is often included in metadata. So, for example, if you entered into a data sharing agreement with a collaborator, you should record that data was shared by a particular organisation, under which terms and conditions, and then any subsequent processing of that data should be recorded in that provenance itself. So it's a detailed history of what's happened to that data over its life cycle. And finally, metadata should meet domain relevant community standards. So, yes. So if we have to apply this to our own field, including uncertainty budgets, methods, and calibration history within metadata, or I should probably say include links to these elements. Applying clear licenses to permit reuse within defined boundaries of our data. To provide enough detail to support future regulatory, research, or industrial need. And for us to try and document deviations from procedures to avoid future misinterpretation. I have a set of relatively high level and practical steps. I think it would be good to develop a fair implementation roadmap tailored to sort of high value data sets. I know that within MPL we're looking at how do we make all of our research data fair, and they're developing quite a comprehensive program to that at the moment. Defining a harmonized set of metadata fields for all measurement data, which is only one sentence, but that's a massive amount of work, and I don't want to understate how that conversion of our traditional process, that there's quite a lot of effort that would have to go in there. Assigning persistent identifiers to data, maintaining that version control, which is very important. Choosing a repository supporting access control, metadata, and automation. Setting interoperability standards covering formats, units, and vocabularies, and that's very important. There's quite a lot of work going on around the world on that topic in particular. And probably a key element is training staff and integrating FAIR into standard operating procedures, so it's not just about data experts, it's something that everybody adopts in their work. And yes, so there are some examples of FAIR in practice metrology. Perhaps for time, I'll go through this quite quickly, but as I've mentioned, digital calibration certificates, machine readable formats, structured metadata, some reference material characterization data sets stored in version repositories, and interlab comparisons that use structured templates. So there is a lot of this that's going on. It's not completely new. It's something that people have been adopting in pockets here and there, but there's probably a lot for us to do before we can say that metrology is fair. And some of the challenges here are that legacy data systems may not support that metadata or identifiers, so there may be quite a lot of work to convert our existing data infrastructure to something that's fair, that adheres to the FAIR principles. Staff may need support to adjusting to these additional documentation expectations. If they're used to a different way of sort of not providing that metadata, they will need some support and training. Access control is something which is important for any interaction with data. And yes, so resources can be limited, so it may be that incremental adoption is required rather than wide-scale revolution. Yes, so that's everything I have for my presentation. I think that the FAIR principles complement our quality culture, and they will enhance our data. It will support our digital transformation and future measurement systems, and it should make it easier for us to collaborate and ensure that long-term value of that vital measurement data that we're all producing. Most data is not fair, most data processes are not fair, but it provides an ambition that we should stick to. So thank you very much. I'll now bring in Daniel to chat about the Forum MD task group. So thank you very much.
So thank you very much, Paul. Do you have my slides included, or
yes,
shall I
yes.
share my screen? Okay, then please go on to the next slide. So I'd like to add a little aspect on the data quality in relation to FAIR, because today, if you look at scientific and technical communities, it's always seen as a combined question, how to make data fair, how to assess data quality. In general, as Paul said, FAIR principles, using them is to foster the reuse of data. In the sense, data is the oil in the 21st century to create value. And when we ask ourselves, what do we use data quality for, then it's clearly to use it to determine the fitness of purpose of data for reusing it. in different scenarios. However, today our communities are tackling several challenges. One is that the reuse of data, it's not deterministic. So data could be reused by many other communities in different ways. So it's not easy to say what data quality information do we need to provide. And on the other side, we have many different dimensions and views. So there's no common standard for data quality, but we have multiple guidelines we are dealing with as metrologists. And Forum MD Group is looking at and working on creating a better understanding of the role of metrology regarding data quality and fairness, but also to understand and provide requirements for data quality for the digitalization in metrology. An important step on this way is to do some landscaping to see where are existing definitions, guidelines, and standards for data quality, and bring up practical examples showing how is metrological data quality established. Next slide, please. Thank you. So we already found over 20 guidelines providing details on data quality. Here's a selection and standardization. We have, for example, General Guideline Series ISO 8000. It's over 20 parts describing different aspects of data quality and common vocabularies. ISO 5259, for example, it's quite new. It's detailing data quality requirements for machine learning and AI applications, but we also have existing guidelines for software products and quality control from ISO IC. In addition, in different domains such as pharmacy, medicine, we have, for example, Alcoa Plus principles, also representing data quality, also pushed by Food and Drug Agency and European Medical Agency, for example, to apply these principles. And we have also different research activities and projects like the TEF M4AIM in Europe, also looking at data quality specifically for training medical machine learning and AI applications. And there was a publication recently by colleagues from NPL, from Russell Miller, comparing several standards. And as you can see on the right side, the overview. So on the y-axis, you have different guidelines, and the x-axis are different dimensions of quality. And you see quite a lot of gaps between aspects of quality these standards look at. And certainly as metrologists, we will ask ourselves which of these dimensions are relevant for us and which gaps we may need to support to close here to establish better data quality assessment. Next slide, please. Thank you. And concluding, so we will focus on better understanding the gaps between these existing standards, especially also gaps in the semantics used to describe data quality semantics. So we know very well measurement accuracy, but ISO standards have, for example, a complete different understanding of accuracy in the sense of trustworthiness. So we have to find out where are the similarities and differences, but there are also different concepts that sound very similar, like timeliness, contemporaneous, resolution and time, and there are also unclear definitions of syntactic and semantic completeness. And for us in metrology, it's certainly interesting to see how do we not create the next standard for data quality, but how could we, for example, align to the existing standards? How can we show how metrology aligns? And one important aspect is certainly to show how metrological traceability is linked to data quality information. It's not only relevant to foster interoperability in the sense of the FAIR principles, but also an important information, metrological traceability, to quantify the quality of measurement data in our case. And of course, here we could help as metrology community, also various other communities outside metrology, to in the future unambiguously assess the quality of our metrological data. And that's already my conclusion to this. It's a way to go, but a very interesting way, and data quality is in close relation to the FAIR principles. Thank you.
Lovely. Thank you very much, Daniel. So I'm now going to move quite quickly to our next speaker. So I'd like to ask Giacomo Lanza if you're able to share to start sharing your slides. Giacomo works for PTB in Germany and has a background in molecular biophysics and environmental sciences. Since 2008, he's working as a research data manager at PTB, focusing on metadata standards, data management plans, and RDM in metrology. And he stepped in at the very last minute, so we should thank him for doing that. So thank you very much, Jaco, and take it away.
Thanks for the invitation. Actually, what we present now, it is the work of my cooperation project with 13 European partners. So I think everybody should be ready somehow to tell what we are doing. Anyway, I just wanted to follow up what we were saying, that the FAIR principles are, yeah, I say, some abstract directions, but don't give the details. The details in the practice can be declinated depending on the application case, and that is what we are trying to do in our project. So, so first I spent 2 words about us, then I will highlight some of the services and the head forms which we offer to our scientists. So, yeah, this already said, we are 14 partners in Europe. Some are more active, some others are have more time limitations, say, and but we often get some input from outside. We have very different expertise. Some come really from the research and also have experience in leading projects. The others are experts for digitalization, for for computational sciences, for information science, and they are always open to new members. And so what we are doing in our project, we want to close the bridge between metrology and research management, because on one side we see that, as I said also before by Daniel, so metrology has a lot of expertise and a lot of clear guidelines and clear requests on to define high qualitative data, and also concepts like traceability and reproducibility, and we want to bring this expertise inside the regulation for research management. On the other side, of course, while doing research methodology, we are also submitted to the rules of the funders, and then we are here primarily to support our researchers to fulfill these obligations painless and also with some understanding what they are doing. And so our present focus is the funding program by the European Commission, Horizon Europe, which declined in metrology, is called the European Partnership for Metrology. But also on the long term, we want to we have a vision how metrology should deal with research data and to make them usable and to reuse them. And we are trying to work in that direction. Yeah, yeah, I think it's the central concept, as I said before by Paul, is yeah, metadata essentially. So how to describe the data, what information we need to make this data reproducible, and yeah, this is one of our fields. So here I try to summarize a little how data are generated and transformed along the so-called research data lifecycle. And then on the left side and on the right side, we have somehow a clustering of the tasks which determine the working with data in a research context. So we have some tasks connected to documentation of the data generation or transformation procedure, the organization, administration, the long-term storage, either as a publication, so open data, or internal storage as so in form of archiving, then legal aspects and also planning aspects. And they are all actually tasks which every research group is already doing with their practice. But what is being expected from outside is to harmonize this practice, to simplify data exchange, to improve efficiency, and to avoid data losses. And here is how we imagine a research activity, research project from the very beginning, from writing the proposal to then starting the project, generating the data, and then bringing the data, and then ensuring the data to be stored properly through publication or archivation, and the numbers mark the positions where we are already working and offering some help. And the numbers refer to our work packages, which of course change over time depending on the demand. At the moment, we are focusing still on guidelines and checklists for digital management, policies, dissemination activities. This number 4 is planning essentially, so DMP and project proposals. Then standards for methodological information and metadata for data publication. And we have the project has been existing for nearly 7 years, and we have already produced some output, which we try to make public on our website. So, for instance, we are working on a guideline, which should be finished in the next trimester, and together with we want to have a guideline as a full document, and then some excerpts on it on the website. And we also organize some training modules nearly every second year, so to address the project coordinators and explain them on which aspects they should focus and which tools they can use. Then we have some recommendation of sample text for the proposals and some sample text for data management plans. And for data management plans, we also made an implementation on the data management plan platform called RDMO, which should enable on one side to choose the right answers and with guidance with the help text, and also possibly to reuse parts of this form later as a machine readable object. Then we have some recommendation for metadata for data publication, involving the minimum metadata which you need to register the OI, but also the metadata requested by the funder, or also some metadata describing the content from a methodological point of view. Then we had a work group dealing with machine readable representation on numeric information. So this is work that, of course, is being done also at other position in the methodological landscape, also CIPM, so the metadata schema for units, uncertainty, etc. And we just work on some use cases on it. And then, so most of these outputs are dedicated to researchers or project coordinators. The one which tries to go to an upper level is the work package on RDM policies, which is directed to NMI leaders. Yeah. So then let's have a look at an example at the DMPs. Okay. First, you must distinguish between the text which is written in a proposal, so before a project becomes concrete, and then the data management plan itself, which is written in the current European funding line in the first 6 months of a project. And yeah, you can perceive it as an exercise just for its own sake, or can it perceive it as a useful instrument which helps you focus on different actions which you need to perform. And yeah, and for us, this advantage comes out when the DMP, instead of being a static document in Microsoft Word, becomes a structured object made on a platform like DMP Online or RDMO, which we are using. So first, as I said, an online platform helps you choosing the right answers, also give you more multiple choice answers, and then it allows you to write it cooperative, and then the information is not just exported as a document, but it stays online and can be exported in different other contexts, for instance, by data publication, or to start automatically some operations. Yeah, we chose RDMO. It is produced here in Germany. It is open source and it is highly customizable. And there are already some dedicated catalogs for Horizon Europe, for the German Research Society, etc. And we created a questionnaire specific for metrology, so for this EPM call, and we let it host in the Technical University Darmstadt, who has better expertise. And yeah, here I can spend more time on RDMO if I still have time. Yeah, this platform has a workflow. So first you choose the questionnaire which you want to answer, the so-called catalog, then you fill it, and then you can export. Also, you can choose different templates for export, and one of them is mimicking the template by the European Commission. Yeah, the same. Another useful thing which you could do with this RDMO, we can also define questionnaires with another focus different than from DMPs. For instance, we have a cooperation with MathMet, the metrology network for mathematics, and then we try to implement their quality assessment tools. So they created some questionnaires to assess the quality of data sets, of software, and of guidelines, and then which first allow a more complete documentation of data, software, etc. But also they try to quantify the quality in a numerical scale, so actually ordinal scale from 1 to 4, based on two ingredients that are the complexity and the criticality. And this is an example which can perfectly be implemented in such an online platform like RDMO. Yeah, we skip a little. Then, yeah, what we are still doing is also to accompany some specific projects to learn what they are doing and to get some general rules from them. And some projects were really advanced on the system management and create some guidelines or checklists on their own. And then what we take is to take these guidelines and try to generalize them. And yeah, and yeah, so this is one ideal workflow how data management could look like. So we have the data flowing from the generation, from the instrument, which is fully digitalized, and then it goes through different processing steps to get the final data in the final states. And they also go through, for instance, evaluation software, an electronic lab notebook, and each of these steps writes down some information. This information actually is metadata, and it is enriched at every step. So one part of verification in our mind is also to gather all this metadata, to keep them in a format which is readable, and then reuse at each step the metadata which are needed. For instance, some metadata for publication, some other for archiving, some other for further working, etc. And yeah, for that purpose, we collected a minimum set of metadata. You see, this minimum, actually, the table is a little too big to be read. Sorry for that. But so this is a collection of about 33 fields, which should be enough to fulfill most general applications. So data publication, data evaluation of data quality, and so on. And also focusing on some metrological specific information, so like the metrology area or the traceability to the SI, as well as the data quality. Yeah, so in the years we also try to expand different directions, and in the time before the SI digital point was created, we also started working on metrology terminology, because we saw we think that this is a core business of metrology, to define terminology for metrological information, but still the information, the recommendation are fragmented and non-uniform. And so we started thinking about which is the essential information that methodology should deal with and make available in a machine readable form. And we made a little collection, and I think could be also a nice activity to perform now in this context. Yeah, so this was a rough overview of what we are doing, and yeah, I'm happy to be here and I'm open for questions.
Many thanks for that, Giacomo. I think this is really quite exciting and vital work. I think one of the recommendations from our task group has been that, as we've both said, the FAIR principles give a goal, but what we need is practical examples for the field of metrology for people to follow, in order for people to actually demonstrate adherence and to see an improvement in the processes. And I think a lot of the work the group are doing are developing that. So thank you very much. Yes, I don't know if there's any questions right now anybody has for Giacomo, or if you wish to leave them to the end, we're going to have a question and answer session. So I'll just open it up right now if anyone has anything they wish to ask. Mark.
Okay. Thank you so much, Giacomo. That was a fantastic, exactly as Paul was saying, a fantastic practical example about what's actually happening, how you did it, the trajectory for what the benefit analysis. Yeah, it's exactly what we needed. I wonder whether you could add a little bit, or I guess give me some comment on how you've found the implementation costs, as it were. So obviously these things are a change process. How did you sort of manage the implementation costs and what they were? And probably also more important for me, how you managed the change management process, because you've shown a really comprehensive system that clearly provides benefits, but staff and scientists, it's a new thing for them, to be locked down into a process, additional workload, et cetera, so they have to see the benefit to themselves and so on. I'm wondering whether you had some sort of, for instance, auditing for compliance, or sort of review of people's work to say, hey, you're missing out on the A bit of FAIR, you need to improve there. In other words, you can't manage what you can't measure, as it were. Metrologists are good at measuring. How are you measuring your performance on this FAIR trajectory so that you end up in the place you want to be? So it's the costs and how you manage the transformation or the change management process.
Yes, thanks. Very, very important questions. And yeah, I confess that you are putting the finger in the round. Yeah, you're right. The implementation cost is one question in the MP, and we always asked for numbers. The only number that I found somewhere was 1 person per month per year, well, 1 person times month, say, for a middle-sized project, but it is not yet a quantification. We know that there are some services which are most services are free of charge nowadays. Some in case the data are very big and need to be uploaded to a special repository, there can be some cost for that, and also the additional storage, which should be bought at the beginning of a project. This can be costly, but it is really difficult to get a cost estimate, I must say. Yeah, this is an open question. We can also discuss in a broader circle, we'll say. And the change management process, so you mean the advantage that our products bring, or how far we are from the aim?
Yeah, what I meant there was you had to start somewhere and you had to bring these principles into play. So you presumably have to there was training, there's probably some auditing and review process, there's probably some feedback to say you're missing the goal, you're over delivering. There must be a loop there to bring you onto compliance, as it were.
At the moment, it's all very informal, I would say. So we bring our output, the researchers use them, and then often we get some feedback from the funding agency, Euromet, if they are satisfied or not, and then we get somehow an informal feedback. So as a form of reply. But of course, we could, yeah, we could make it more professional and more methodological. So for that, I also open for suggestions.
Great. Thank you very much. That was an excellent answer. Thank you.
Thanks.
Thanks both. I think we'll leave it at that for now. But please, if you have more questions, we'll have the question and answer with all the speakers later on. But that's great. So thanks, Giacomo. I'd now like to invite Christian Paredes to present slides. Christian is the Liaison Officer for Digital Transformation at the International Liaison and Communication Department of the BIPM. It's a master's degree in chemical sciences and began his career as a chemical metrologist at National Metrology Institute of Colombia. Joined the BIPM in late 2025 to contribute to the development of the SI digital framework and to support the BIPM in becoming the digital anchor of trust for the metrology community. So please take it away and present your slides, please.
Thank you very much, Paul. I hope you can see my slides now.
Yes, they've come up.
Good, thank you. So we have been having very interesting topics about how do we want our data, our metrological data, to be specified consistently, and the outcome of this is that we can use it ourselves in the future, and not only now when it is fresh, but also that other people can use it regardless of these other people not being. Just let me hide this. Or I don't know if I can hide this. Okay, I will just leave it. So we want our data to be useful for us in the future and for other people in other places, and not only us in the future and other people, but also our computers and other people's computers, regardless of their operating in different systems with different programming setups. So this is what all the FAIR principles are about in metrology, to take the most out our data and out of the measurements that are so costly to perform. So this is not only a metrological community issue. This is also to relevance to many institutions, to many international institutions of the international scientific and quality infrastructure, and they all recognize that we all needed a common framework in which we could make use of digital measurement data, being this data fully machine actionable, and that it will have a digital representation of the SI that the machines will understand and that the machines will be able to operate on. And this is the SI digital framework. So the purpose of the SI digital framework is to incorporate all these FAIR principles in the measurement information and in the measurement data, so machines can use it and machines can communicate in the same under the same terms as we have been doing so in the analog era, using a common international system of units that is the SI. So this joint statement of intent has been there for a while now, and in response to this joint statement of intent, the General Conference of Metrology specified of weights and measures specified which features should this SI digital framework have. So it included, as I mentioned, a globally accepted digital representation of the SI. And from the beginning, it was told that it should fulfill the FAIR guiding principles for digital metrological data. and to facilitate the use of digital certificates. And the purpose of this is that these machine readable and actionable data, as the CIPN mentioned, should support digital metrological traceability of this information. So we have been told that provenance is important. We as metrologists understand the relevance of metrological traceability and how it enables to trust our data and to know if we can make informed decisions based on this metrologically traceable data. And yeah, that's what the SI digital framework is intending to do, to provide a common framework for all digitally managed data, so they can all interoperate under the certain terms that are compliant with the concepts and the definitions that have been that have been accepted in this 1.5 century of modern metrology. So the SI digital framework was defined as a 3-layer infrastructure where the core data services were defined by the CIPM, and the VIPM is the steward of these core data services. And so this talk will focus on the core data services that are being implemented by the VIPM. With the help, of course, of many leading institutes, national metrology institutes. So this core services layer has metadata modules and digital references. A metadata module can be seen as a blueprint for organizing data, for structuring data, and so it will include all the details of how do we want this data to contain the information, which information is required for this data to be considered like complete, as we were listening to Giacomo in the last presentation. And the digital reference is one of the outcomes of trying to fulfill with one of the FAIR principles, with the findability principle that we will see later on. And this applies mainly to units of measurement, to types of quantities, and for metrological traceability. So regarding units of measurements, we have the SI reference point, the SI reference point, which is one part of the core services layer of the SI digital framework. So the SI digital framework, it's like the big umbrella that covers all the services, and the SI reference point, it's this part of the SI digital framework that relates to the digital representation of the units of measurements and all the concepts that the units of measurement have. So the purpose of this SI reference point is to serve as authoritative digital reference for the SI that is described in the brochure, in the SI brochure. And it has a web page that maybe you have explored by this moment, and it describes how is the information organized in this SI reference point. How is the effort from the VIPM to make the machines understand how do these units of measurement interact to each other, how are they defined, and how they can be used for the measurement data to be expressed under common terms. So yeah, as I mentioned, the purpose is to enable machines to manipulate the information in a way that is compliant with the SI brochure. So the SI brochure, it's I will say the most important document, the most important technical document in metrology, being only, I think, the most important, the Metro Convention, but the most important technical one is the SI brochure, which states the concepts that we assigned to a value of a quantity, a unit of measurement, the defining constants of the SI, the unit prefixes that we can use to change the value of the units. But more than that, more than being a simple depiction of a glossary term, it also has relations among those concepts. It has rules that we need to follow to combine and use units and prefixes. And it has rules for expressing values of quantities. So what the SI brochure contains is knowledge, and this knowledge it's made available to machines using ontologies. An ontology it's a formal specification of knowledge from a defined domain of science, and these ontologies might be represented using graphs like this one that you can see here, and these graphs contains nodes, the circles, and contains edges. And this is a very tiny part of the ontologies that are described in the SI reference point, and it helps us to see the relationships in between the terms. And more than that, because we can read the SI brochure for that matter, it helps machines to use that information to make to consider the semantic rules, the semantic content of the SI brochure, and to apply those rules for the measurement data and then operate on that data, and to really understand and apply like the axioms, the logical axioms of what is good and what is not good when expressing a value of a quantity. For example, those are classes and properties and attributes that define all the knowledge that is contained in the SI. For example, here in purple, you might not read because of the font is too small, but in the purple we have the defining constants. So these defining constants are grouped because they belong to the same class, defining constant, and they are grouped by this red node that is the class of defining constants, and they relate to the units that are not depicted here, the SI base units. Which in turn relate to other units. And for example, here in brownish color, we have the prefixes that also pertain to the same class and an SI prefix. And those also have an attribute that it's the scaling factor, which is a property. Each prefix will have a scaling factor, and those scaling factors are the power of 10 that we use to enlarge or diminish the value of a measurement unit. And then this information can be used by the computer to make new relationships, as we will see now, that enable all this information to be machine actionable. And there is we have been told several times that there is no fair principles without machine actionability. So what we want is the machines to be capable of making decisions based on information without human supervision. So the rules that are expressed in the SI brochure should also apply to the SI reference point, and there are like constraints, for example, that we cannot use two prefixes in the same unit. Yes, that there is not such a thing like a millimicrometer, for example. For that matter, we use nanometer in that example. So the computers must be able to identify these logical actions and to apply them to the information that we are feeding to our databases or to our digital calibration certificates or to our digital certificates of analysis. So it will be compliant with the SI brochure, which is the rules that we all as metrologists should follow. And it will also make that all systems could interoperate in between them without them necessarily using the same ontologies, without them necessarily using the same languages, the same schemas. because that's what the advantages of these ontologies are, that they are highly interoperable as long as the relationships are clearly defined. So not all the relationships in between the properties and classes and attributes that are defined should be not all of them should be written explicitly, because some of them are implicit and the computer will draw the connections automatically when it is integrating these knowledge bases into the systems. So here is an example of what we were talking about, this knowledge graph. We have classes, for example, here, an SI measurement unit. And this has several relationships with other resources, like SI colon has definition. So a measurement unit can have a definition, and it has an attribute that it has a symbol. For example, the mole has a definition that is based on the Avogadro number, or the Avogadro constant, sorry. And the attribute is that it has symbol MOL, the mole. And we can have the same for all the concepts that are stated in the SI brochure. For example, the constants, the defining constants can have units. So it will relate to other members in the same ontology, and it will have attributes that it has a value, for example, which is the numeric value that was defined in the constant when the SI was redefined 6 years ago now. So how this SI brochure and the ontology of the SI brochure help us fulfill the FAIR principles, and how is the fairness of this SI reference point? So we can see in Paul's presentation that the FAIR principles, the FAIR guidance principles, are four main. They are specified further in 15 principles that are steps that allows us to say, like, yeah, this data is findable, this data is accessible. And to be findable, for example, we have that data and metadata should be assigned a globally unique and persistent identifier. So in the case of the SI reference point, it does so. It provides persistent identifiers for the units. For example, units colon mole for the prefixes, prefixes colon micro in this example, and for constants. But more than that, also to the decisions that were made to adopt those concepts, to assign values to those concepts, to the resolutions from the General Conference that were also used to adopt a definition of a unit, and all these PIDs that should be used with a namespace, with a prefix that you can see here at the bottom of the screen. They define persistent identifiers for data, so we can unequivocally tell a machine that if it sees units colon mole and units has been defined as sidigitalframework.org/si/units, then it will know that a mole is different from the animal mole, for example. So it will be capable of having semantic criteria to differentiate concepts that are similar, that might have the same name, for example, but and it can operate on them, so it will not produce like unlogical data, which is the purpose of what we want the computers to do. We want them to produce useful data. And other principle for our data to be considered findable, it's that it should be registered or indexed in the searchable resources. So to fulfill with this, the SI reference point exposes its persistent identifiers in the web. So the ones that we saw in the former slide here are resolvable through HTTPS, which uses the HTTP protocol for communication, and it can retrieve the information that is contained to that unit. For example, for the mole, it will give us the definitions, the value, the constant that is used to define those. And yep, this helps us to make our data findable. So to be accessible, one of the principles that we were told this morning was that metadata should be retrievable by their identifier using a standardized communication protocol. And to allow this, the SI Digital Framework has disposed APIs, application programming interfaces, where machines can communicate with the machine here, the VIPM that hosts this service, and can retrieve the information using standardized protocols. So these standardized protocols should fulfill certain requirements. For example, here that the protocol is open, it's free, and universally implementable. So here we can see an example of one of the communication of one of the responses that a machine will receive from the VIPM if the machine is trying to access the information of the SI units. So this response body here, it's depicted as JSON, which is only one of the possibilities. There are more possibilities. It can be other open formats. And this is, it's free, it's software independent, so you can open those files with any software and you can operate on them on different ways, and you can translate one format into another format, and it will also make your data interoperable, as we will see later on. Right now, I mean, to be interoperable, data and metadata should use formal, accessible, shared, and broadly applicable languages for knowledge representation. And to this, we take advantage of a very active community that has been working at the World Wide Web Consortium, the W3C group, that it's the organization that is making the internet accessible for machines. So they emit recommendations about which are good practices for the data to be internet friendly, to say so, and many of those recommendations have been adopted by the team that implemented the SI reference point and the SI digital framework, like RDF, resource description framework, which is a way to express ontologies, as well as all ontology web languages. And it uses other ontologies that are already established, that have like a common accepted meaning in the communities, and that can all be linked. So when we talk about the author of a publication, it's everyone will know what an author is, without having more further context about about the publication itself, about asking to clarify. But this is in case of publications. But for measurement data, we can talk about provenance. How was the data generated? So for provenance, there is another ontology that I missed to put here. That it's also one of the W3C recommendations, and by using this, we stick to commonly used languages, commonly used by the community, and it helps us make our SI reference point interoperable, and it will also help you have your measurement data interoperable by means of using the SI reference point, which is what we encourage. And to be reusable, there are some aspects, like the metadata should be richly described with a plurality of accurate and relevant attributes. So here is how one of the possible representations of the SI reference point knowledge bases look like. We have the definition that it is an ontology for the web languages, and that it has been created at some point, that it has a license that tells people, if the people and machines, of course, that they are allowed to use this under certain terms and conditions. And this is part also of the accessibility layer, that accessible doesn't mean open necessarily. In this case, of course, it means open because the BIPM wants everyone to use this to foster equivalence and to make everyone talk under the same terms. But to define a license for the metadata model, it's important, so we can describe how is our ontology, what is our ontology allowing to do. And it has also information about provenance, about who generated this file, when was it generated, what was the source file that used it, and yeah, all the relevant attributes that should be incorporated. It's still a work in progress, and yeah, we hope that it will help the SI reference point to be more reusable for all the metrological institutions and all the international intergovernmental institutions that are also paying attention to this. And yeah, close to finish, one important thing is that FAIR, as stated as findable, accessible, interoperable, and reusable, has also been referred to by the authors of the paper as fully AI ready. So making our data fair, it's also helping into AI to objectively understand this information and to have systems that can have a deterministic traceability path of how was a response generated, how was a calculation generated. So it can be audited, and yeah, it can be traced back to the source in a consistent manner that will not break metrological traceability principles, that it's the main purpose of the SI digital framework, to allow digital metrological traceability to be implemented consistently. So going again to how does the ontology looks like in the code. Here we have the base unit definition declared for the mole. So this is the information. This is part of the information that is assigned explicitly to the mole. It is declared as an SI-based unit. It has a preferred label in English and in French. It has certain definitions that have changed over the time. But we keep the historical ones because one of the principles that we saw in Paul's presentation was that the metadata should be still available, not even if the data is not there anymore. And yeah, the good thing is that the authors of the SI reference point knowledge base have defined what is in the SI brochure, all the SI-based unit, all the SI special name units, like the Newton, like the Pascal, all the SI units, not all the non-SI units that are accepted for use in the SI, like astronomical units or hours for time. And as it is a semantically consistent module, then the machine has been also been programmed to generate other kinds of compound units that have not been explicitly defined, but that then are provided a persistent identifier. Like here we have a density of electric current intensity, ampere per square meter. And this was not made manually. This was generated programmatically in a consistent way. So it is defined as a product in between two units, where on the left side you have the ampere, and the right side you have the per square meter. And And the square meter is defined as a numeric exponent, which is the -2, and the base for this, which is the meter. So this is consistent with the algebraic constraints and the algebraic regulations that have been specified in the SI brochure, and by using this, you are making sure that your metrological data is using the correct measurement units. Of course, all of these can be written in the full PIDs, in the full persistent identifiers, using these prefixes that are defined here. But yeah, you can choose which representation fits better your needs and your current use. This is easier to read for a human, and yeah, it makes no much difference for a machine. And again, this is also software independent. So this is a text file that can be stored for a very long time without it getting like issues of back compatibility to other softwares, and it can be operated from several frameworks for several softwares. And yeah, the other core services the other services of the core services layer of the SI digital framework operate and are being defined in the same way as ontologies, depicting, collecting all the knowledge, defining formally all the knowledge that is contained in the KCDV service categories, for example. Because yeah, those units are related to quantities that we measured, and same quantity types should have consistent units that can be also be automatically checked for consistency by the machines. There is also one service that it's also being underpinned by a knowledge base. This is the nuclides metadata model, which is used in ionizing radiation, that also enhances the interoperability of the measurements of ionizing radiation. And regarding the interoperability layer of this nuclides metadata model, it connects to other persistent identifiers that have been already been used by the chemical community. For example, the INCI and the INCI key that are already established, but it does not cover all the nuclides, but cover many of them. So it opens the door for the nuclides metadata module to be capable of accessing other information that is not strictly contained there. That might be in other databases like PubChem, for example. And regarding metrological traceability, the SI reference point has the SI digital framework has a resolver for KCDV CMCs, and this resolver will provide with the machine readable information about the CMCs. Will also provide persistent identifier for your CMCs, and that's information that you can incorporate in your digital calibration certificates, so you can then have like the seal of the CIPM MRA digitally for your digital calibration certificates, which will make like a very strong statement that this calibration has been done by a trusted member of the international metrological community, that it is compliant with the CIPM mutual recognition agreement, and that it has been audited under a very strong process of that is the one that ends up in the CMCs being approved in the KCDV. And as long as the metadata should still be available even after the data it's no longer there, once the CMCs are no longer valid, still their metadata will remain in our database. So digital calibration certificate that is 10 years old, that has a CMC that has been renewed a couple of times, still that persistent identifier from the moment in which the DCC was emitted it will be accessible in the future, and it will be declared as a CNC that was valid from one point to another point. So it will help the machine to validate whether the digital calibration certificate was valid at the moment in which the CNC was active, for example. And also to support metrological traceability, the SI Digital Framework is incorporating information for the mise en pratique that are what the NMIs use for the realization of the SI based units. At the moment, yes, we are working on the mise en pratique for the meter and for the mise en pratique of the temperature scales. And this information is being placed in the machine readable format, and in the future we hope that it will integrate seamlessly with the SI reference point. That is the purpose of all of this, to produce that will be self-consistent and that will be stable in time, and that can be used for all measurement data to be fair, to be fully AI ready as well. That it's a topic that is gaining more and more importance in this year. So all of this was developed by the expert group of the task group of the SI Digital Framework. Here you can see their names of current and past members. I apologize if I miss someone. And yeah, we will love to hear your feedback about this, your requests, your special use cases that might not been yet considered yet by us, but that are important for the community and that might need updates of the SI reference point. So here we have issues, an issues page that where you can file a complaint or a recommendation or a question. We are pretty welcome to all the feedback from the community, and if you want, if you don't want to have a GitHub account, and you can simply send me an email, and we will be happy to hear from all of you. So yeah, that will be all. Thank you.
That's fantastic. Thank you very much. It's really important work. I know a lot of people who I know some members of the task group, and I think it's going to be something which is only going to grow in its impact over the next few years. So thank you very much for that. In the interest of time, I might go straight on to the next presentation. If people have any questions, please put them in the chat. But I would encourage you to follow some of the links there, and we should hopefully be able to make the slides and links available to people afterwards. So yes, thank you very much for that. I would now like to ask Rodolfo to present his slides. Rodolfo Gomez Rodriguez is the Chief Technology Officer of the Instituto Nacional de Metrología in Colombia. He has a degree in economics and master studies in applied statistics and project management. He started to work in metrology in 2018 as a general secretary, and since 2023 is responsible for coordinating digital transformation topics in the NMI. So yeah, please take it away.
Thank you. Can you see the presentation?
Yes, thank you.
Okay. I'm trying to present the regional experience, specifically about what's happening in the Americas. For this, I want to introduce this understanding about digital transformation stages and how we are trying to develop the first stages that are involving digitization. This is very important because we need, as you can see, we are trying to see how can we improve the digitization for information, how could be it organized. CIM is a regional organization of metrology that is composed by most of the countries of the Americas, and in the past years is working about M4DT initiatives toward digital calibration certificates, automation, and it's very important for the next things. One of those initiatives involved with the cooperation of another regional organizations that we could understand and build some device or some devices for the measurement of environmental conditions. In that moment, 6 countries developed a thermohygrobarometer, and the challenge there was that that device operates through IoT, and for that it was necessary to build a platform that could get the data and could show the data. That was the scope in that moment. In the region, we have subgroups, as you can see, and it's very important that we are part of a subgroup named ANDIMET. There are 5 countries right now. And having this advance and having this opportunity, we have been talking about understanding about data quality, and yeah, as we can see, having in mind the Data Management Association framework for data governance, we are here expressing 5 out of 10 components that are important in the maturity of a data governance for an organization. Those are data quality, architecture of data, the metadata, reference data, and analytics. That it could be an opportunity after we achieve some levels of maturity in that data governance and in the other components. There is a reflection about how could we involve a relationship between data quality and FAIR principles. There are at least close to 60 dimensions that are being named in data quality, and we try to understand how could those dimensions, specifically these that we are presenting here, are being related with the FAIR principles. So we can see that certain dimensions of data quality are directly involved with some of the 4 FAIR principles that we are talking right now. After that, trying with that understanding about the implementation of FAIR, how is very important, how could we handle the implementation of data quality? We saw an opportunity. We have been working, especially ANDIMET has been working under some cooperation spaces. In those cooperation spaces, we had the opportunity to talk about digital transformation strategy and certain obstacles that we are having in our NMIs. And for this time, we see that it's necessary to have the measurements of environmental conditions in an NMI, but not in laboratories. It's important to have for risk management, get the data from another spaces, how as could be where we have power plants, or where we have data centers, where we have material reference products, and it's important. this joining the laboratory. So we saw that the capability about measurement in environmental conditions are being developed by each unit of production, if I can see this here. So each laboratory normally develop the solution for the measurement of environmental conditions. And this brings obstacles or difficulties in interoperability, because we can see that we have different data models, and it brings difficulties for building a data infrastructure or data models or an NMI data model. So we have different spaces, different solutions, and different data models. So we are trying to begin with arrangements where we can identify which are the data models in each unit, and how could we begin to develop under that point of view of the data governance framework, that we begin to build some standardized infrastructure data infrastructures, sorry, and how could we help to be replicable, and how could we build solutions that could be useful, so we could reuse the solutions that are built, and we can begin to have an opportunity to use this in spaces that are in each NMI, but this has the opportunity to have a solution that could help another NMIs that have maturity levels lower than others, and it will help the new opportunities for interoperability when we are talking about DCCs or digital passport products that is now to be involved in the development of the QI bodies in each country. So right now we are with the support of a call from SIM. We have some resources for a pilot where we are trying to manage a lot of variables and trying to build a data structure or a data infrastructure that can be the same in the 4 countries. In this case, is Colombia, Ecuador, Peru, and Bolivia, NMIs, and we are defining a main space, a very similar space. In this stage, we are not involving laboratories yet, but with the expectation that we can use the platform that in a beta stage we have at SIM, and this could help us to have that harmonization of structures of data. And after that, SIM has the expectation that you could use that platform with another models that could help in analytics. One of the main topics that I saw before, I presented before, and with the challenge about dealing how could we handle the data sovereignty, and that is in the part we are right now. How could we solve that? And that's a short brief of what are we doing in the region and what are the expectations that related about this project.
Sorry, taking me a while to sort out my screen there. Thank you very much. I think there's, I think one of the motivations for this webinar, as Nikita has described, is that there are different regional experiences with FAIR and the implementation, and it's good to hear about the different initiatives that are going on. I think we have, so thank you very much for that. I think we have approximately 15 minutes left to do a bit of a roundtable discussion. I'm just going to share some slides. I'll just be 1 second. So hopefully you can now see my screen. If I could ask the speakers, Nikita, Daniel, Giacomo, Kristen, and Rodolfo, to stay on, and we can just go through a couple of questions that are some of the ones that we described via email, but also I think we have a question in the chat from Mark. If anyone would like to ask a question to the group, then please type that now, and I'll try and get that asked. I don't know, Mark, if you want to ask your question out loud, or I can read that out for you. It's up to you.
Oh, yeah, it's okay. I'll just, I'm sorry, I'll just find it. Hang on a minute, just give me a second. Bing, bong, okay. Yeah, so thanks, Christian. It was a great example of how BIPM's work on ontology, semantics, and structured data can really minimize the ambiguity in our communications in our digital transformation, and give us clear, as you said, deterministic, definitional, and provenance clarity for our data objects, and make them the highest value that they can be. What we're selling trust and reliability in the NMI universe, and this really adds to that. I'll just ask a question here. I guess it's maybe a slightly sideways question, but I noticed that in other areas of digital transformation, people are adopting what I'd call AI system mining of relatively unstructured data pools where data is just chucked in, and then there's clarifying information in the form of explanatory texts, definitional documents, etc., often in plain text. And the AI just sort of reads through the definitions, finds the ISO definitions, interprets the data in a sensible way, and comes to conclusions in a sort of a unstructured way. Anyone who's used ChatGPT or Gemini will know the sort of thing I'm talking about. I wonder whether, Christian, you could comment on or others could comment on this tension between having a very exact but somewhat fragile system. It's a bit like a computer program that will break if you get a right bracket in the wrong place, but on the other hand will guarantee you accuracy, important for KCDB and CMCs and so on. And the tension between that and this more practical approach that lots of AI people are using of it's a robust system, deals with ambiguity very well, but sometimes has errors in it that it might be appropriate, for instance, for cost-critical applications or research data or stuff for which quality isn't quite so much a challenge. So there's a tension between having it really tight, but that's really fragile, and having it a little bit looser in the definitions, but more robust system. Can you talk through your thoughts about that tension?
Thank you, Mark. I will say that in metrology we have said for many years that metrological traceability is one of the most important properties of our data, because we want to make decisions based on information that we can trust and we can trust if we know that it is comparable. And the generative AI, that I think it's what it's the one that can be used for robust but with potential ambiguity. Reading at your question, I think it's still it will always be like a maybe too much too creative, and it is difficult to get where it is getting the reasons to comment on something. It is like it produces hallucination. Everything it produces, it's based on statistical probabilities. So it is difficult to trust. What I have seen, it's like some sort of hybrid systems in which you fit your ontology to a computer, and then on top of that you add a layer of deterministic language, so you can communicate with your ontology through an agent, but the responses from that agent will be based only in the graph that you fit him or fit it. I must say that this is way beyond the scope of what I've been preparing so far. But I take the opportunity then to invite you to the next forum of big open event in 1 month, exactly in March. Just before the Forum MD meeting, there will be a workshop on AI. So on the afternoon will be a breakout session on semantics and AI. So you are more than welcome to join. It will be an hybrid event, so we can have further discussions about this tension in between these two topics there. Thank you, Mark. Thank you very much.
Great. Thank you, Christian. It's a great answer. Thank you.
Does anybody else on the panel wish to comment on that, or should I go to one of the other questions? And then give a second. I've just seen a question from the chat here. Will the Vim be reshaped into a digital framework similar to the SI digital framework? Don't know who would like to answer that.
I think it is from the VIPM core services. It should at one point be also be involved in the SI digital framework. One of the projects in the middle term of the VIPM, it's to make the information of the Vim machine accessible, machine operable. So short answer, yes, but we don't know exactly when. Thank you, Ellen.
Does anybody else wish to comment on that? Perfect. So we'll go on to the next question from Benjamin here. So it says, when we refer to persistent, is there a defined length of them we want these references to be around for years, decades, or centuries? Especially for organizationally hosted persistent identifiers, there is a cost associated with that persistence, hosting sites, APIs, databases. It could be a problem in the event of changes in financial situations. So I wonder, Giacomo, if this is something which you've thought about in some of the work that you've done at all. For the length of time some of this stuff would have to be available.
So I know that so there are some regulation by the funders, for instance, that say that the data should be accessible at least for 10 years. And then there are some situations where the data are legally irrelevant and they should be conserved for about 30 years. But of course, what we are working here about is about long-term knowledge. Therefore, I suppose that also a longer time scale is convenient. Maybe so. As a temporary answer, I could say single data sets, maybe on the order of a few decades, but reference data sets or reference vocabulary, schema, etc., they should so already in the direction of century.
And I suppose that's a good answer. And I suppose also one of the principles as well is that creating metadata even when the data ceases to be exists. So it is having that metadata that exists. So it's not necessarily hosting the data for all time, but having that metadata that would describe what the data was to be persistent. So maybe there's a lower cost associated with that type of process. I'll go to the next question here, which says, at present, we can see some features of Industry 5.0 that will be more directed to the quantities related to people. Some measuring systems include not only data obtained from sensors, but also from experts and testees. Is it planned to find opportunities to consider them as fair data? Daniel.
Maybe I can comment on that topic. So first of all, Industry 5.0 is, let's say, the human-centric Industry 4.0. For all who wonder what Industry 5.0 is. Indeed, it is considered to also make this data fair, and communities, especially in human science, are already working on standards doing this. Of course, in this case, it's data about people, their background. Additional policies have to consider being relevant in the region where you work. In Europe, for example, we have the GDPR regulations providing rules which information on people to share. In the medical area, we have these assessments too of ethics to make sure the data is anonymized or let's say curated in a way that it's suitable to be published in a fair way later on.
Perfect, thank you. I think we have two questions from Yanis here. I wonder if you want to choose your favorite question of those and ask, or I can choose one for you.
Either way, so I don't mind.
Okay.
I would think that I would stick to the second one as it is applies to everything. So long story short, we say that we keep metadata for the good reasons we want to keep them, but obviously keeping them forever, it's effectively keeping data, metadata as data, and so on. So chicken and egg situation. So the long story short question and maybe discussion point, is there any good practice out there, or should we be thinking that all such metadata should have an end of life and defined by a contract, digital contract, and in a sense that after so many years we delete them, so we don't keep on occupying thousands of terabytes somewhere in a data center, or that the end of life is when a specific process uses this data, converts it into information useful for business, for example, and then we delete them from that point onward. Thank you very much.
So, does anyone like to tackle that? I think if there are no volunteers, I think you're correct. It's not about storing all things for all time. There is a cost associated with it, and over an extended period of time, a large organisation keeping all of the metadata similarly will attach its own cost. I suppose it is. You've probably answered the question yourself as you've described. I think it is. Contracts describe the sort of useful life cycle of the data and the data associated with it, and making some choices over whether this data is suitable for future reusability, and if it is, then that data that you'd like to keep. So it is about perhaps deciding upfront about that life cycle, particularly if you're talking about data that's associated with different partners, probably it would be entering into agreement with those. I'm not sure if anybody has a more sensible answer to that from the panel.
It does make sense to me, Paul. Yeah, thank you very much for your support. Cheers.
Cheers. Oh, sorry, is my microphone is not working. Sorry. So that was a different message. I hope my it's coming through. otherwise, so I have a message about the microphone. I can try for the afternoon to use a headset. But on that topic, I think we've come to the end of the webinar itself. So I would like to thank everybody for attending the webinar today. It's been really interesting, even though we've spoken about the topics beforehand, it's been really interesting listening to everybody, and really good to see the practical examples of fair implementation in metrology. We have recorded the session, which should be made available afterwards. And yeah, I think a couple of people are telling me I'm not very audible. So I wonder if Daniel, if you can take over from me. Apologies, but well, essentially, thank you very much for attending the webinar, and please thank you to all speakers and Gemma for helping us out, and please contact Daniel and myself if you have any questions. So, thanks. Bye now.
Thank you to all.
Thank you. Bye.
Bye.
Thank you, everybody, and thank you, Paul, for moderating us through this very nice webinar. And also from my side, thanks to all of the speakers and participants for your great contributions.
Thank you. See you later.